get started here as a few folks are joining us. Hello, everybody. Did I just say forks are joining us? I meant folks. Yeah, apparently I need to take a breath, take some caffeine, and settle down. But yeah, so the history of this class, I developed the first version of this class in 2007 when I was at the University of Nebraska in the Department of Psychology. I was there for 8 years, and then I moved to the University of Kansas, where I had a home in an interdisciplinary department, but I still taught a lot of psychology students. And at the University of Kansas, I co-taught this class, with Jonathan Templin, who was an ed psych at the time. And we traded off. Each person did it every other year. And when he did it in R using Levon. And when I did it in M+. So because we were trying to keep that synchrony between the two different versions of the class, they were cross-listed across our departments. The examples that I'll post are literally going to be the same examples in both programs. And so for that reason, you have a full version of what I'm going to show in M+ using Levon instead. For homework 2 and 3, you are able to use Levon for any of that. It starts to break down in the latter half of the course when we get to IRT models. Differences in estimators yield slightly different options and sets of results, and so then it will become more of an issue. And just as foreshadowing, I know several of you are Stata aficionados. Let's see, folks I haven't said hello to yet. Lexi, Megan, Kelly, G1, I think the other people. Hello, everybody. Jordan, I think you snuck in the middle there. Sorry, Stata people. I have a slide on this, but I wanted to give you the bad news. I figured out the hard way after several hours of trying that Stata does not have a way to correct for non-normality of your indicators at the same time you have missing data in its SEM routine. So for that reason, the results that I would show you in M+ or Levon would not match those of Stata, and so I did not make Stata examples. But that being said, if you still want to learn how to use Stata to run these models, I do know enough to be able to help you. I'm not going to be able to make a comparable set of examples using Stata because the numbers won't match and that will be confusing. So I'm just not going to go down that road. So if you haven't done so, grab the stuff from the website that goes with this next section, and hopefully we'll get a chance to start it today, but if not, next week for sure. All right. Any questions? Logistics, comments, anything before we dive back in? No? Are you ready to rock and roll? Yes? It's 2 o'clock in the afternoon and we're going to be excited. Yes, we are. I know it's raining outside. Is it still raining outside? Anybody know? Yeah, it's one of those days when it would be nice to take a nap, but you guys chose not to take a nap. You guys chose to come here instead. So thank you for not taking a nap until after class. A 3:30 nap could still be doable, right? Depending on how late you stay up at night. I'm a parent, and so, a 3:30 nap would mean that I wouldn't be able to get to bed, and that would be all kinds of bad, but earlier in the day, perhaps. All right, so I'm back in lecture 3 on my big screen here, and just wanted to do a little bit of review before we finish the rest of this. So we've been talking about reliability, the idea of consistency in measurement. A measure is reliable if it gives you a consistent version of the story. So to what extent, if you took more different sets of items, if you took it over and over again, would you get the same sort of result? That's the idea of reliability. People will provide evidence for reliability by giving different versions of the test and correlating the scores between them. So that's alternate forms. They may give the same instrument over and over again and correlate the scores across repeated measures. That's test retest reliability. But I would say by far the most prevalent estimate of reliability comes from Cronbach's alpha, or Gutman-Cronbach alpha, if you want to believe that Gutman got to it first. But either way, I want to just reiterate what alpha doesn't tell you. Alpha does not tell you anything about the underlying dimensionality of the items. It can't, because there's nothing that goes into the formula that would pay attention to differences in how the items relate to each other. So alpha, the most condensed version, is right here. It's a function of capital I is for the number of items or indicators, and R bar here is the average inter-indicator correlation. So there's nothing in here that captures the variability in how items are related to each other. That would guide you toward potential pockets of these items measure one thing, but these items measure something else. It doesn't know. So it has to assume unidimensionality. There's no way to test it until you get to a model in which that becomes a disconfirmable hypothesis. It also assumes that items are equally discriminating. So we had some questions about this after class. You can lump all of these ideas and words together as one concept. So the assumption of equal item discrimination is the same thing as saying items all have equal covariance with each other, is the same thing as saying tau equivalence. I'm honestly not sure where that term came from because tau is going to be a different thing than discrimination in the models where we get to, but that's just a phrase that is used. True score equivalence is another word that means the same thing. Briefly, it means that alpha assumes without testing that all items are equally related to the latent trait. They're equally good. That may be the case in certain contexts. It's rarely the case when the items are not exchangeable computational kinds of things. And then also related to unidimensionality, a stricter version of it is that the errors are also locally independent, meaning that there's no correlation between the errors across items. And that is also a testable hypothesis within the framework of latent trait measurement models. So those are the things that I want you to know about alpha. All right. Any thoughts or questions about alpha? Or reliability for that matter? No?
I think I have one.
Hit me.
Okay. I'm not sure I can phrase this though. I'm gonna try. Okay, so I just want to make sure that I'm understanding equal discrimination
Okay.
accurately. So when you say that, well, when you say all the things you just said,
All the things, yes.
is that the same as saying that it assumes that all of the items measure the same level of severity?
So I just saw your question in the chat window, so sorry for missing that. No.
Okay.
So items have two different characteristics that we will pay attention to, and the way that we define them differs across measures, but one of those characteristics is discrimination, which is the thing we're talking about here, how related the item is to the trait, how good it is, sort of colloquially. And the other is difficulty slash severity. And that's the location on the trait. So, like, what kind of person is that item designed for? And alpha says nothing about that.
Okay, so that is just not covered in the assumptions here, right?
Right. It's not relevant. It's in the strictest definition, that is the case. So in the article about alpha, I think there's some text in there where McNeish states that alpha assumes items are normally distributed or continuous or things like that. And then some of the clapback articles said, no, that's not true. Um, Anytime that you have one reliability coefficient, you are saying that everyone is being measured equally well. And the only way that that can be true is if your items are actually continuous, such that the information that they provide could keep going. So I think that there's nothing that's necessarily associated with difficulty or severity that has to do with alpha. Like it doesn't absorb that information. The means are not part of the formula. But in practice, that's another reason in which alpha can be inappropriate, is to the extent that you need a different reliability coefficient as a function of your location on the trait, then alpha would be problematic for that reason too. Okay, that makes sense, she says. Good. All right. Okay, other questions or comments? So yeah, alpha means you have enough items. That's what alpha means. If you want to have better alpha, just get more items and it'll pop right up there. The converse, if you have a terrible alpha, that is bad news. It's hard to get a bad alpha, but if you do, that's not good. All right, so then we talked about sort of the correlations that go into these things in general. All of these indices of reliability and item discrimination are using Pearson correlations, and the same is true even if you have binary or ordinal indicators. So to the extent that Pearson correlation is not a good way to represent associations between binary items, reliability is going to be downwardly, I don't say biased, but it's going to be low as a consequence of that. And so the latent trait models for binary responses that we'll talk about later in the semester are going to use a different kind of correlation to solve that problem, what's known as tetrachoric correlations for binary items or polychoric correlations for ordinal items or polytomous items, as they call it. There's another vocabulary word. Polytomous means categorical. It's usually meant to describe ordinal responses. And then we talked about interclass correlation a little bit as yet another kind of correlation that's more appropriate if you want to pay attention to differences in means and variance across the dimension that you're trying to get reliability for. And then we talked about attenuation corrected correlations. That was, let's see here, slide 29. I think that was about where we left off, right? More or less. So reliability in a perfect world. So it ends up that if you try and compute an attenuation corrected correlation, it can go over 1. This is like the example from the paper where it was initially conceived. The problem with this, it lies in just the reliability portion here. If your reliabilities are that low, it becomes suspect to try and extrapolate what the relationship would be between the perfect versions of those constructs anyway. It's just too far away from the data. So the more reliable your measures are, the less you would even need to do some sort of reliability attenuation to look at how they're associated with each other. So let's start then on slide 30 as new content. What are standard errors or what are reliability coefficients for? They're to give you standard errors. So I know that the University of Iowa provides measurement training that's much more extensive than at previous places that I've worked. So this is sort of your lowest level, like what's a standard error mean and where does it come from? I realize that there may be more, what's the word I want? Adaptive, I would say, ways of computing standard errors that take into account the fact that they should be conditional on the level of the trait. But this is sort of your entry level point in thinking about what does a reliability coefficient mean? Like, does it really matter if your reliability is only zero point 0.7 or does it really need to be zero point 0.8 or zero point 0.9? And the question can be answered by thinking about how does reliability translate into any individual's likely score, and how wide of an interval around that does lack of reliability create. So I have some real world examples here to illustrate this, but if we think about the idea of a reliability coefficient, what it's supposed to tell you, whether it's alpha or KR20 or Spearman Brown or whatever, right? It's supposed to tell you the proportion of variance in the total scores that is due to real true score differences, right? The part that's signal relative to noise. So if I have a reliability coefficient of zero point 0.8, that's supposed to be 80% good variance and 20% error variance. Well, I can use that information to figure out how much of the total score's variance is error variance, and then take the square root of that error variance to form an error standard deviation. And that thing is known more generally as a standard error of measurement. And I can use that standard error, the square root of the error variance, to compute confidence intervals around a given score. So if I go with a classic 95% confidence interval. If I assume that my sampling distribution is supposed to be normal, then my critical value for that interval would be 1.96. So look at these two situations. Let's say that I have a total score for my sample that has a variance of 100. We'll make the math easy. And for the person that I care about, they have a score of 50. Okay. So if my reliability is 0.91, that'd be really good, right? That's a high reliability coefficient. That means that it would be 91% signal and 9% noise, 9% error. If I take the square root of that, I end up with a standard error of 3. So if I go 2 standard errors around my score of 50, so just using integers to make it easier to follow here, that would work out to be an interval of 44 to 56. So that means that if that is the interval that would describe 95% of those intervals would have the subject's true value, their true trait level. So if they got a score of 50, you can't take that at face value. They didn't get exactly 50. They got somewhere between 44 and 56 95% of the time. Like you can think of it as like the bubble around the score that you have to take with it. If you compare that to the same setup, a total variance of 100, an individual who got a score of 50, but what if the reliability was only 0.75? Well, that means it's 75% signal, 25% noise. Square root of that is 5. That gives me an interval of 40 to 60. So what if I want to decide whether or not a score of 50 meets some cutoff? Let's say that on this scale, anybody who gets a 58 or higher has a problem, right? There's a lot of scales that work that way, that if you hit some cut point, that you're deemed that something else needs to happen to you because you are too high. And let's say that that was 58. Well, if I look at this just at face value and I say, well, they got a 50, they're fine. Eh, Not really, right? If the reliability is 0.91, then that 44 to 56 says, okay, yeah, the 50 is under the magical 58 cut point. But if the reliability is lower, if the reliability were only 0.75, then their interval actually includes that 58. So really, you'd want to figure out like what is the end of the interval that would not include 58 and make your decision based on that. So what reliability is enough, I think in part depends on how precise you need or want to be. And in research settings, where you're simply trying to get some sort of score on a variable to measure something, and you're trying to measure a lot of somethings, and you're looking at associations amongst those somethings, I think the stakes are a lot lower as to how reliable any one score needs to be than if you're giving subjects instruments to measure them and you're making some sort of high stakes decision, right? Like if you need to pass the bar exam, you want your standard error to be as small as humanly possible. That way, no one sues you. There's lots of examples of licensure tests and things like that where you have to hit some standard. And so, what the standard error of measurement is needs to be as small as possible so that there's no ambiguity as to whether or not a person met some standard. So, classical levels of reliability that are good enough, like 0.75, may not be good enough for the purpose in which you're trying to measure a trait. And as I noted on the onset, this sort of classical way of going about this assumes that the standard error for every person is the same. But we know that's probably not true because people who are very low on a trait would need a lot of items of corresponding difficulty or severity to really distinguish just how low they are. People really high on a trait need corresponding items of the opposite type. So if you have a scale that's designed in the traditional way, where you want items of mid-range difficulty because those are the items that have the least range restriction that can show the best discrimination, those mid-range items are going to measure mid-range people. And the people on the tails probably aren't going to be measured as well. So the idea that there shouldn't just be one standard error means there shouldn't just be one reliability either. And I know there are ways of computing what's known as a conditional standard error in classical test theory, but that's often one of the benefits of moving to a latent trait framework for items that have boundaries like ordinal binary items, that you can get a flexible version of reliability that actually pays attention to how many items you have at each corresponding level of difficulty, and that's what creates your reliability function as opposed to your reliability value. Okay, so here's a real world example that may be near and dear to your hearts. You you all had to take the GRE to be here, right? Does anyone not have to? Anyone? No, so I remember taking the GRE. It was a long time ago, but it was the first time that it was adaptive. And I remember sitting down at the GRE verbal section and realizing that things were not going well when the items started being things like black is too white as, right? There's nothing like a little proprioception that you're tanking to keep your confidence up and your score up. So, long story short, I didn't do that well on the GRE. I still got into graduate school and eventually I still got a job. So who cares, right? There's all sorts of arguments about whether or not the GRE is valid, whether it actually predicts graduate school performance, whether it predicts eventual graduation rate, and the data on that are not terribly compelling. There's lots of evidence that people from underrepresented groups do disproportionately badly, or that certain skill sets that are measured by the GRE may be more or less relevant in certain fields. It's also the case that it doesn't measure very sensitively at the upper range because it's designed to be an entrance exam. But did any of you get a standard error of measurement as part of your printout or your email message? No, right? You just got a number, right? And so that's the same problem that we're talking about here. Well, I got a 50. Well, really, did you get a 50? Or did you get somewhere between 40 and 60? Or did you get somewhere between 49 and 51 to where, like, yeah, you got a 50? Well, the people who make billions of dollars administering the GRE and other things, ETS, testing, educational testing services, I think that's what it stands for. They put out a guide every year to the guide towards GRE test scores. So I downloaded this year's guide and I created the following figures. Deep, deep within the guide are the standard errors of measurement based on their data. So you know that these errors are probably the most possible optimistic versions because they're put out by the company who makes money on this product, right? So, but even if we take these at face value and say that they're accurate, these are the 95% confidence ranges around each of the scores. I have stopped paying attention to GRE scores so long ago that these numbers don't mean anything to me, but I'm guessing they might mean more to you. So if you got, say, a mid-range score, the test goes from a score of 130 up to 170. The standard error of measurement at 150 is about 2.5. So if you go two standard errors out on either side, a score of 150 actually corresponds to somewhere between 145 and 155 if you were to take this test over and over and over again. That is over a full standard deviation in the population. So the standard deviation of the verbal score is 8.5, right? So the standard error at the mid-range of the score, where arguably it's the most important because that's the range at which people would be iffy about accepting you because your score is, not good enough. The standard error creates an interval that is a full standard deviation. Now, the fact that these are optimistic, I can tell you just by looking at what happens out here. What happens if you get a score of 170? Where does your interval go? Can you have a score of 173? Nope. How about down here if you get a 130? The interval is even wider. So the fact that these intervals are of different sizes means that there is a function of differential reliability across the trait. And the fact that the intervals are narrower up here is a consequence of there being relatively more items, it looks like, this is what I'm guessing, that are of high difficulty. They're measuring higher people relatively better than they're measuring lower people. And that's probably a strategic decision on their part because if somebody gets, the lowest possible GRE score, they're probably not getting in no matter what. And so we don't need a lot of precision down there. We need a lot of precision at the top. So these are the standard errors that create the confidence intervals on verbal. Here's what it looks like for quantitative. They're a little smaller than verbal, but about the same pattern. So yeah, so the next time that I guess if you're ever in a faculty meeting someday and you're talking about applicants and it's like, well, this person got a 150, but this other person got a 154, you should raise your hand and be like, yeah, that's the same. That's within the standard error of measurement. And there's actually a whole nother table where they have standard error of differences that are even larger than these, where they talk about how different two scores would need to be able to say they're actually different. So how much reliability that you want, more is always better, but how much is enough depends on what you're going to do with the scores. If you're making decisions that affect people's livelihood, then too much reliability is never enough. Here's the link, by the way, if you'd like to check this out. It's real data from the people. All right.
So
So
can I ask a question?
please.
So when you talk about differentiator SE, so the CI becomes different based on the score. So when score becomes high, more relevant. So can I say that one measurement has that kind of various reliability?
Reliable, yes. According to their data that they have published in this guide that's linked below, the higher scores are more reliable. They have a smaller standard error to them, which creates a narrower confidence interval. So there's a table in here that actually gives you the standard error at each of these 5-point uh, in increments of 5, I should say. And the standard error for quantitative, for instance, ranges from a minimum of 1 up to 3.5. So the minimum of 1 is up here, where 2 standard errors on either side is only a total range of 4 scale points, whereas down here it's much larger. So yeah, you can say that a score of 170, according to them, is measured more reliably than a score of 130. So this also foreshadows the idea of which items should be selected to be part of an instrument should be guided on who you want to give that instrument to. Do you want to measure high people well? Do you want to measure low people well? Do you want to measure everybody well? So that means they must be asking difficult questions, right? Since the higher ability items have a higher reliability. Yes. That's what I would infer is that they have um, relatively more difficult questions. So they have a giant item bank that they pull questions from. And I believe more recently that it's not adaptive per question, it's adaptive in sets of questions. But it looks like the higher questions are more discriminating or they have more of them. I can't be sure based on this data, but you can say that the higher scores are measured more reliably than the lower scores. Yep. All right. Other questions, thoughts? So yeah, anytime that you're dealt with a score in life and decisions are made about the score, the first question you got to ask, what's the standard error? Because that will tell you how much you should believe in that score. And standard error comes from reliability. So wrapping things up here on the reliability side. So the idea of creating a sum score, the add shit up model, as I'm fond of saying, you are assuming unidimensionality And indices of reliability make additional assumptions about the item discrimination or uncorrelated errors. Because all items are treated equal to make a scale more reliable, what kind of items do you need? More. What kind? Better items? No, more. More items makes your alpha increase. So this is a nuance that we'll pick up through the semester as to what kind of items make it better and better for what purposes. And at the most basic version of using a reliability to compute a standard error, it's assuming everyone's measured equally well. And that's probably not the case. So from reliability to validity, so I'm going to do a little bit of hand waving here. I'm just going to put it out there, right? This is hand waving at its finest. If you took the GRE twice and got the same score both times, that is good. You must have been in the reliable section. I only took it one time because I can only afford to take it one time. And I figured I wasn't going to get any better. So that was my background on that. So we talked about dimensionality, which is a precursor to reliability, which is in turn a precursor to validity. We're not going to spend a lot of time on validity this semester. This is going to be pretty much the end of the story because all of the latent trait measurement model focus is on dimensionality and reliability. Um, you can think about threats to validity, though, in different ways, having to do with the part of the total score or the trait estimate that's due to error. If you have error that's generated by random processes, that's going to be a threat to reliability. But if you have error that's generated by systematic processes, that could be a threat to validity, meaning you've measured something else besides what you want to. And that then would cause relationships of your trait with other things to be off as a consequence. So, a classic example of this is acquiescence bias. You have people that want to say yes to things or to agree with things, and it differs across ages and it differs across cultures. And so, one might be wary in the way that they create questions as to not create questions that you have to agree to everything. That's part of the logic of having differently worded questions, for instance. Um, I'll give you an example from my personal experience. If you think about the latent trait of like athletic ability. So I am a runner still, but I used to do cross country and track in high school. And whenever the weather turns cool like this, it always makes me think of cross country practices, and I get a warm glow in my heart because I loved cross country so much. Arguably, you could use our performance at our cross country meets as indicators as some sort of latent ability, right? Like if you have better ability, you should do better at the meets. With one exception, if you're someone like me and you tend to choke because you get so nervous that you end up running more slowly because you're afraid you're going to run out of energy and you don't actually hit your potential. That happened to me a lot. I actually ran better in practices when there was no consequence to doing badly than I did in meets. So if I wanted to think about my race performances as a measure of my athletic ability, I would argue they're probably not that valid because there's this sort of lack of confidence thing that's being measured at the same time. So it's not that you can say that a measure has validity or is valid. Wording like that will get you yelled at by an editor or other people to say that a scale's been validated because it always depends on what you're trying to do with it, whether or not you have evidence that it can be used in that way for that purpose in that context. But all of the things that we're going to do this semester with latent trait models are going to inform us as to whether or not a set of indicators is measuring a thing or multiple things, and to what extent they're measuring that thing well, reliability coefficients, how much of it is error, signal versus noise. But none of that tells you about validity. Whether or not you've measured something the right thing is validity. And that's a much harder argument to make because it almost always depends on external data. So a long time ago, one of my students made these pictures, and I really like this as an idea. The middle picture here in particular is a situation in which you have high reliability but low validity. You've measured something well, it's just not the right thing, right? That can happen. And what happens in practice when people select items to measure a trait is that if you're only going off of the item statistics, if you only go off of how correlated the item is with the trait score with each other, you'll tend to remove items that are less correlated, but they probably measure different aspects of the trait, right? If you're trying to get sort of a well-rounded picture of a trait, then you may want to keep some of the items that are less related because they may potentially help you triangulate on a more valid version. So there's always this sort of juxtaposition of higher reliability, but you don't want reliability for the wrong thing. Um, it used to be that people would say that any validity coefficient, so the relationship of your trait with something it's supposed to be related to, can only be as large as its reliability, but that's probably not true in practice. So that's not something that I would necessarily worry about. In terms of where validity evidence comes from, it's almost always external, which means it's almost always subject to problems. There's a lot of ways that you can end up with validity evidence that is problematic, even if there's really nothing wrong. Um, the only way that I can think of that provides validity evidence from internal to an instrument is the extent to which the ordering of your construct, so the idea of a construct map from a couple slides ago, the idea that you can order people in terms of their standing on a trait, and you should be able to order items and their responses in terms of a standing on a trait, to the extent that you get data back that match, that you can predict ahead of time which items are going to be more difficult, and to the extent that you can also specify a prediction model. So if you have features of items that you know lend them to being more difficult or more discriminating, that provides internal evidence for construct validity. I used to have a lecture on that in this class, but we're not going to have time for it. But if you're interested in that kind of internal evidence, there's a field of models called explanatory item response models. And I did a lecture and an example on that actually in the clustered multi-level modeling class because right, random effects are latent variables. So it worked out that it was in that class. So I have a link here to that material if you're interested. But other than that, validity is almost always evidence for validity is almost always collected from external sources. And because I'm only doing a very brief hand waving out of duty at this point, I want to put in a plug for Steve Dunbar, who's supposed to be teaching a seminar on validity in the spring. That way you can get into it in a lot more detail than what I'm going to do here. So for a long time, people argued about how many kinds of validity there were and what all was necessary. And so there's a long history of people's taxonomies of, well, you have convergent, discriminant, and content, and face, and construct, and all these kinds. Um, the ones that I'll talk about are sort of the ones that have stood throughout the ages. I'm not going to get into debates as to how many kinds there are or how many distinctions. What do you mean here? Those of other constructs? I missed the root of that question. Can you clarify, please? Waiting for the chat window. Slide 36. Uh, yes, those of other constructs. You mean relationships between other constructs? Is how we provide evidence for validity in most cases. Yes. So you can have internal or external evidence for validity. Internal evidence can be um, corresponding predictions of item difficulty that actually, so you can predict why some items are more difficult, and that gives you some sort of theoretical evidence that you know what you're measuring because you know what makes it harder or less difficult. External evidence is just the extent to which your measure of the trait relates to measures of other constructs in predicted ways. And there's all kinds of ways of demarcating that and labeling it and categorizing it, but that's literally what it boils down to. Um, so the classic ones, predictive and concurrent. To what extent does your measure of a latent trait relate to some sort of undeniable future or current criterion? That presupposes that you have something that it's supposed to relate to, which is not always the case. Um, so, for instance, if you have a long form of a scale It's just called a scale at first, but then you want to make it shorter, right? So then there's a long form versus a short form. Criterion related validity would be to what extent does your short form do as good a job in terms of its relationship to the long form. So that would be one instance. Admissions tests predicting subsequent school success and that kind of thing. One thing to keep in mind in all of this is differential ranges of sensitivity are going to limit correlations. So if you have a measure and the current measure is designed for people of relatively high abilities. So in the instance of the grant that I'm working on, for instance, if you're trying to measure pre-reading skills, say in kindergartners, first graders, people who know their letters, people who understand what sounds letters make, and they're sort of transitioning into being able to read, measures that are designed for that population are going to be too hard for children who haven't gotten those skills yet. So if you develop another measure that's designed explicitly to measure the lower end of those same skills, it's not going to be related to the current measure very well because they're targeting different populations. And so to the extent that you have differential ranges of sensitivity, that can limit how related two measures of a trait are, which then limits the evidence for validity, even though it's not really a problem. So there's a lot of ways that sort of these kinds of external, how related is my trait to something else can go wrong, even if like validity isn't the problem. Differential sensitivity is one of them. The big one, it tends to be what's known as construct validity, the extent to which it's measuring what it's supposed to. This is almost always the case in practical research where you don't have like a gold standard to compare something against. It requires some sort of theoretical framework. So these are the classic ways of demonstrating construct validity. Show that your measure is positively related to things that it should be related to, and show that it is unrelated or negatively related to other things. So that's known as convergent or discriminant validity. You have to be able to find those relationships in a sample and explain why they're useful. And so that's where a lot of arguing based on theory as opposed to data is relevant. So ways that this can go wrong. Um, it's really easy to mess up a validity study. One of the things that can happen is that you don't have decent reliability. So if you don't have reliability, it's hard to show validity evidence. You have to have a signal first before you can show how the signal relates to signals of other things. Um, it could be that you've misguided your theory. So if you're saying that my measure is supposed to be related to this other thing in a positive way, it could be that you're wrong about that association or that you don't have it in the sample. Um, Things can change over time. So this is particularly why you can't say that a scale has been validated. I know people write that all the time, but it's something not to say because it implies that there's a cut and dry, like it's done. Like I have validity and it's over now. And that's not always the case. Indicators may need to change over time. A couple examples of this that are relevant. Do I have anything here? So the word pen, like the thing you write with, pen, there is linguistic dictionaries of versions of words that are like the primary version or like the extra version because pen could also be a place that holds your dog, right, Kayla? Your dog could be in a pen. Now, which one of those do you think is dominant? The thing you write with or the place where your dog lives? Yeah, I think it's the thing you write with, but at one point it was the place where your dog lived, right? That was the dominant definition. There's a measure of social class that is given inside the general social survey. And one of the items is, do you leave the house without a handkerchief? Not a pocket pack of Kleenex, mind you, which I never leave the house without, but a handkerchief. Because people who leave the house without handkerchiefs are heathens, right? That's an item that may have worked in 1930 or whatever, but it doesn't work today. So things like that. Here's another example. This is a mouse, right? is mouse the animal the dominant definition or mouse the computer mouse? Right? Mouse the animal would have won up until maybe 1985 or something, whenever Windows came out. Then mouse this is much more. So things like that can sneak in to make it so that your measure may no longer have validity because of the way that the indicators have to adapt to different times or different cultures or different uses. It may be the case that the theory of the construct evolves, and so back in the day there may have just been, affect, and positive was one end and negative is the other end, and nowadays that's insufficient. You can have positive and negative affect as a two-dimensional space that would require new measures, and so a measure of affect as a single dimension may no longer have construct validity because the theory of the dimension has changed. Response anchors, another thing that may need to be adjusted over time to maintain the same level of reliability or the same level of validity. So just try the big picture here is try never to say that reliability or validity is a property of an instrument. What you can say is that evidence for reliability has been provided by, right? Evidence for validity as a measure of this for this reason has been provided by. Evidence for is the way that you would cite previous research without getting into trouble. Just don't say validated because it's not true. So there's my hand waving for validity. How was that? And that's it. Validity is over. I'm getting the dreaded my internet is unstable. The Zoom is angry with me for waving my hands at validity. I'm sorry, Zoom, but I don't have time to cover more than this because my class is about how do you get the latent trait estimate, right? What it is supposed to predict, what it's supposed to be related to or not related to, that's a whole separate set of issues. And those issues are similar whether you're dealing with a latent trait estimate from a measurement model or whether you're dealing with a total score from just adding items up. So that's a different story. So I'm going to shut that down and I'm going to show you a real life example. So this is example 3, the idea of doing classical item analysis. I'm demonstrating it using 2 different software packages, Stata or SAS. You can also do this sort of thing using the alpha routine in R. I'm sure there's more than one way to do it in R. But this is the kind of information that I'm going to ask you to provide for me in homework 3 down the road. So this is an example to help you get started on that. My stream is freezing. Okay. Am I back? Okay, thank you for letting me know. I just got to learn to like stop talking whenever I see all of you go at the same time, right? Because you freeze too. It's like a two-way street. Okay, so can you see the shared screen still? Are we still good on that? All right. So this is a true story. Back when I was a graduate student at the University of Kansas, I worked in the Research, Design, and Analysis unit for the Lifespan Institute. And basically, that was a one-stop shop for investigators who needed help doing data analyses, designing studies, writing grant proposals, doing results, and all that kind of stuff. So I was working with the Beach Center on Disability there. They're still there, which is why I say these things, and helping to design new instruments to measure aspects of coordination service providers for children and families who include children that have disability and the parents. So there weren't good measures at the time. Oh, we're frozen again. Okay, pausing. Am I back? Now am I back? Okay. All right. We're gonna get through this. This is 2020 in a nutshell. If it's not a power outage, a murder hornet, a forest fire, a hurricane in the middle of Iowa, freezing. We're gonna make it though. We're gonna make it this semester. So anyway, I got to be involved in a whole bunch of scale development, so you'll get to hear about that this semester. So this is a true story from an actual paper measuring the quality of family professional partnerships. So this is a very quick version of a very long scale development process just to illustrate how you would ask for and interpret item statistics from classical test theory. So just a real quick little example here. So we were working with two subscales, things that had to do with the child themselves, so children who have disabilities, like basically how the care providers interact with the child as one dimension, and also how they interact with the family, so that the coordination, the support, and that kind of thing. And like everyone says to do, so this was 2005 when this article was published, so this work was happening in the early 2000s. There was an exploratory factor analysis conducted. I probably did at least some of those myself. And it ended up throwing together a subscale of 11 things as one factor and 10 things as another. So we thought, okay, we're going to start from there, get a new sample, and look at the results to figure out whether or not those items are good enough, whether or not they're sufficient in terms of reliability, and then eventually test their assumptions about unidimensionality. So that was later on in the paper, but this is the background to that. So here's some Stata code to get item descriptive statistics. So just means and correlations between the items, nothing fancy. I am using all available cases so that if I have any missing data, it's not going to be a problem here. In certain programs like SPSS, I believe it limits your cases to just people who have all the items. So that's going to limit your sample in most instances. But we have summarize that gives item descriptive statistic and the thing called PW core, pairwise correlation, that gives a correlation matrix. So these items, here's the 11 items that we're looking at here that are all supposed to measure aspects of services provided to the child. They are measured on a 1 to 5 scale as to how important is each of these things. And what the items actually are is going to be showing up here in a little bit. So, but just staring at this table, note the means. So each item had, except for one, had all possible responses used, so that's good. But what do these means here indicate about the item's level of difficulty or severity? What do you think about that? Let me make this a little bit bigger because I see everybody. Means of 4.4, 4.7, 4.3. Yeah, they're quite similar. Are they on the high side? Yeah, so we would say that they're high difficulty or high severity, even though it's actually backwards. Like everybody thinks everything is important. This is a questionnaire about how important each of these 11 items is to a family of a child with disability. The idea is to eventually measure a family's satisfaction with respect to each of the items, but satisfaction is more of a formative construct in that like you can be satisfied with some aspects and not others. But ideally, if you're trying to measure sort of one underlying system of collaboration, then these are indicators that that system is either high functioning or low functioning. That's the trait that we're trying to measure here, is the extent of a partnership. So these items are all going to be on the high side. That means that most of the people answered 4 or 5. It is a Likert scale, yes. To what extent is the question. Here is what the correlation matrix looks like amongst the items. And this, by the way, was generated using one of my favorite things in Excel. It's called conditional color formatting. So if you paste in the numbers under conditional formatting, you can have these sorts of heat map pictures. And this makes it real easy to tell if there's pockets of items that have lower correlations than others. So if we just look at the range of these things, it looks like they range from about a low of 0.31 up to the greenest one here, maybe 0.7. So they all are related to some extent, but it looks like they vary in how related they are to each other. So I'm anticipating that there's likely to be differences in discrimination just based on this correlation matrix. The good news is that these items do appear to be measuring something in common. So in terms of troubleshooting real-world analyses, this is step one. If you stare at a correlation matrix of indicators that you think are supposed to be measuring the same thing and you don't see correlations, game over, right? If you see correlations of like 0.1, game over, right? Because the correlation between these things is the latent trait. And if you don't have a correlation, you don't have a trait. So you don't even have to do any fancy analyses. If you don't have correlations, game over. So at least we know we have something to work with here. So here's the results from the classical test theory item analyses. It's under an alpha command in Stata, and item level information is provided with this option right here. Suppression is a question from the audience. What about suppression? Those are bivariate correlations, not unique correlations or partial correlations, and so suppression wouldn't be relevant in this context. Suppression is only relevant in thinking about how the semi-partial relationship differs from the bivariate relationship amongst a series of variables. So we have different numbers of observations for each item. Item test correlation and item rest correlation. So those are going to be your indicators of item discrimination, how related the item is to the trait. The trait is the sum in this case. So if we look through these, the item test correlation is uniformly higher than item rest. Do you know why? Surprising or not surprising? What's the difference? Inclusion of itself. And one more item, yes. So item test correlation is the correlation of the item with the sum score, including that item. So it's like correlation of partially itself. Item rest correlation is the total score excluding that item. So it's removing that redundancy. All of these are what I would call decent, pretty good. The lowest one is like 0.57, goes up to 0.8. So that's item 12 here is the relatively strongest. So there's nothing in here that I would say is a huge red flag. The average inter-item covariance with each of the other items is something that's provided here. That's not something I typically see reported, but it's giving that. And this last column, this is voodoo. This is alpha hacking. You've heard of like life hacks, right? Like tips to make things easier, or p hacking, ways to get your study to be more publishable, to hack your significance. Well, this is alpha hacking. And your alpha hacking column, this is what alpha would be if you didn't have that item. So if this is high, that means alpha would be better if you got rid of it. So higher values are worse in this last column here. So you would want to look out for any items that if you removed that item, alpha would jump up a lot. Now I have highlighted in here in bold 2 items in particular. There's nothing that makes these items stand out to me in terms of their item statistics. They're well within sort of the expected range. This one's a little low, but so is the first one. And alpha, if deleted, this last column here is not that different. The reason that I highlighted them, though, is based on their content. So the overall alpha, by the way, is given at the end of the printout. It's 0.91. So that would be considered a good alpha by any one standard. But if you look at the content of these items, let me make this a little bigger. Can you see that? And you can see it in front of you. You have the handout, right? Do you see anything that makes those items look different relative to the others? Why would I have flagged them? Chat window says it's about what the child is doing, not what the parent is doing. Yeah, those are the only items that don't have child in them. Like, just look at the words, right? The word child is not in there. Now, that might beg the question, well, why are they in the child subscale in the first place then, Lisa? Do you know why? Because EFA put them there. That's why. Because we did an exploratory factor analysis and it looked like they wanted to be on this factor, and so that's where we put them. Is it the computer's job to tell me my theory? No, but that's what happened. So hindsight is 2020. I'm probably the one who did these EFA analyses, and I'm just looking at the numbers, right, and going, okay, these items all measure this thing. And when you actually look at the content, you go, huh, those items actually don't measure anything about the kid. And that's what the subscale is supposed to be about. So for that reason alone, we decided to take them and move them to the other subscale that has to do with the family or the parent. So after dropping those two items, we redid the item statistics and everything looks about the same. There's some variability, but no items look terrible. The alpha has gone down, so it was 0.91 before, and now it's 0.90 because we've lost two items. Simply because there are two fewer items, that's right, because alpha means you have a lot of items. So, but an alpha of 0.9 is still acceptable by anyone's standard, so we called it done. And then I fit a unidimensional factor analysis to it, and it actually did hold up, and so we decided we were actually done at that point. So we're going to take those two items that have nothing to do with the child and move them to the other factor. So here's the family subscale, and I did this part in SAS just to give you another program to work from. I don't care what program you use. All of these things are going to be the same. I did have the option on here to make sure that we're using all possible values, so not doing listwise deletion. So I'm doing proc core that has an option alpha. And proc core gives you not only the correlations, but it also gives you means, standard deviations, and such. So you can get all of your item descriptive statistics in one shot. I saved the data set with the correlations to a SAS data set. That way you can report that correlation matrix directly without the N's and P's in the way. So here's the rest of the items. Most of these, with the exception of two, so item 14 and item 19 are the only ones that didn't use all 5 responses. The same issue in terms of the severity or the difficulty. These item means are really high, so most people are answering 4s and 5s on this. Here's the correlation matrix. There's a few things that jump out. Item 20 is redder than the others. If you just look at this, that one looks to be potentially problematic, so you can look across the row or across the column for that one, but we'll see when we get down here what happened. It gives you the overall alpha for the scale, both in the, if you use the covariance matrix or if you use the correlation matrix. In practice, I don't think it matters, but standardized is the version that we'll pay attention to. So we have correlation with the total, and that is the item remainder correlation, and alpha if deleted under the raw variables and under the standardized. And I've highlighted two things here that stand out. The correlation with the total is relatively lower for item 14 and item 20, and you can see what the items are. So and this is the point where we actually had I wouldn't say arguments, but discussions in our research group about these items. Because if you just look at these statistics, the correlation with the total and what alpha would be without them, those items should go, right? They have a lower relationship with the trait. Alpha would go up. Without them, they should go. In the end, the investigators kept them. And they kept them because there was nothing else in terms of the content that addressed these particular nuances of the trait, being honest and protecting privacy. So the trait is supposed to be like the functionality of the relationship between the service providers and the families of children with disability. And there were no other items that dealt with honesty or privacy. So they decided to keep those items, even though the statistics indicated that they probably could have gotten rid of them. So this is an example of the trade-off between reliability and validity. Like, if I were to get rid of those items, I would have improved reliability, but potentially at the cost of validity, because now I'm not measuring the trait to the same depth as before. But this is too long, right? We ended up with a nice tight 9 items. This one is up to 12, and we wanted to try and figure out a way to get them each to 9 for symmetry. So what ended up happening is that we got rid of item, I'm trying to remember which ones they were, 17, 18, and 19. So item 17 right here, 18 and 19. Can you guess why we picked those items? Plans meetings at times and places that are good, returns your messages, and keeps appointments. Any guesses as to why those we ended up getting rid of them? Because it's not the statistics. Correct answer, similar to are dependable. Ding. Those are all ways of being dependable. So we decided that item 23 was sufficient. People who are dependable do what they say they're going to do, whether that's making a phone call or keeping an appointment. Now, if I wanted to measure dependability as a construct more specifically, then those might be items for my dependability scale. So that's what ended up happening. We swapped out those 3 because dependable was good enough. Rerun the analyses. Items 14 and 20 are still relatively low, but they wanted to keep them because they covered unique content. And the alpha ended up being 0.88. And that was that. And the article's been cited 228 times since then. So yay for us. So just an example of a real life version of this. What I'm looking for you guys to do in the data that you care about is identify any huge red flags. Because these kinds of analyses you can always do no matter what kind of sample size. But if you find that people aren't using all of the response options, that's not good. If you find that items aren't correlated, or if there's pockets of correlation where some items look way more related than other items, even though they're all supposed to be measuring the same thing, that's going to hint at what's going to be found by the factor models to follow. So you'll get a chance to practice this in homework 3. All right, so any questions on reliability, classical test theory analyses, and so forth?
Well, just for double checking question.
Sure.
So when you talk about this last column, this one.
This
so
one?
Yeah, so about alpha.
The alpha if deleted.
At the upper page, previous page.
The previous page?
Yes.
The first subscales, you mean?
Yes.
Okay, yep, right here.
So when I want to interpret that alpha, I might want to compare the overall alpha and then decide, right?
Yeah, so if any of these would go up above like what you already have, that's an indicator that that item it doesn't agree as much, like it doesn't play as nicely with the other items. But it's really what I was trying to illustrate here is that you can't just blindly look at the numbers,
Okay. Yeah.
right? Because I had two items that didn't belong in the subscale based on the numbers because EFA put them there. And then I had other items whose numbers were bad, but they wanted to keep them because of the validity of what they're trying to measure. So these are a guide, but in reality, it's a combination of sort of art and science into what makes something good and believable. Good questions. All right. Any other questions? All right, then I lied. We're not getting to lecture 4 today, but we'll be back next week unless there's another hurricane or power outage or God knows what's going to happen by then. But we're going to keep going. That's what we're going to do. So it is not garbage day, which means I say, have a good weekend. Office hours start now if anyone wants to chat. Otherwise, peace out, take care, stay safe.